morning, guys. Today we're going to start our unit on significance tests. So we're just going to go over kind of the components of a significance test, how to get them organized, and then in future lessons we'll talk about the details for specific types of tests. So we've actually worked with significance tests, we just didn't give them that name. Back when we were talking about sampling distributions, we very informally played around with the concepts behind significance tests. So this is similar to confidence intervals in that it's another piece of, or another tool we have for drawing conclusions using those sampling distributions. So here's our problem for today. For her career, Carrie has made 42.7% of her three-point attempts. Since coming back from a serious injury, she has only made 10 out of 33 attempts, which is 30.3% from three-point range. Management's looking to extend her contract, but should they be concerned that her three-point proficiency has actually decreased? Now, this is not a perfect example. We know that we're not perfectly random in this sample that we have. We know that we're not perfectly independent in each of these trials. But this topic is similar to something that you could see as far as we have a proportion and we're wanting to know, is there a change from what was going on in the population to what we see now? Maybe after we've done a certain treatment or whatever it happens to be. So that's how we're going to use this imperfect study. So what we're going to do is called a significance test. They're also sometimes called hypothesis tests. So significance test is just a formal procedure for using observed data to compare competing claims. So we have some type of claim made, and then we're going to do a study. We're going to get observations off of that and compare our observations to the claim. So first thing you always need to do is write a hypothesis statement. So you've used the word hypothesis before in your science courses, right? It's an idea that you think may happen, and then we're going to collect data for it. So it's the same idea here. Hypotheses are what we think the possible outcomes that could come from a study, and then we're just going to test them. So the statements are just a structured way of writing the competing claims. So we're going to put our claims down, and then we're going to just make sure we have a very formal way. And what this is going to do is going to help us with figuring out what type of calculations to do, and kind of how to organize our tests and things like that. It makes it a lot easier when it comes time to, if we're using technology for calculations, to key stuff in, but it also makes it easier for kind of writing our conclusions that we can draw from it. So first thing you always need to do is define your parameter. Well, remember, parameter is just a population measurement. So when we write hypothesis statements, we're not talking about the sample, right? Our claims are not about what's going on in the sample. The claims are going to be about the population. So we need to define what we're working with in the population. So if we look back over, we're talking percentages, right? So we have a couple of percentages. So those are just proportions. So I would use P as my proportion, okay? So as my parameter. So P is just the proportion of three-point attempts that Carrie will ever make. So just out of the entire population of all three-pointers that Carrie will attempt, P is going to be the proportion that she makes out of all those. So we want to know, what is that P supposed to be? What is her true percentage? Is it really 42.7, or is it now a lot lower, maybe closer to 30.3? You know, how does management need to handle this situation? Do they offer a contract based on what she was? Do they try to use this as a reason to maybe get her into a little bit cheaper contract? Maybe they use this as a reason not to sign her at all because she's not doing what they need her to do. So this is just a tool, a piece of evidence that we would provide management to help them make a decision on how to proceed. Maybe we could be working for Carrie's agent, and she want us to figure out if this is evidence that there's something wrong, that she needs to kind of go through a different rehab, or maybe they want us to show that, okay, this could just be kind of fluky, streaky, and she really is still up here, and it's just a random chance issue. So there are a lot of different ways this information could be used. So when we're writing our null hypothesis, your null hypothesis, the first claim, is just a statement of no change or no difference. So what this is the devil's advocate position. We're going to say, okay, I know the sample shows this, but let's say, we'll let you pretend that you guys are right, and we'll show you that this still isn't that big of a deal, even if you guys are right. So that's what we're talking about with null hypothesis. It's a statement of no change or no difference. So we're going to use our parameter, P, and if it's no change, no difference, if we're saying, okay, you guys are right, then you're always going to use an equal sign. So a null hypothesis always uses population information that means variables and calculations. So always uses population information and some form of equality. For us right now, that's going to be an equal sign. There will be situations later on when you're going to, there will be situations later on where it could be a greater than or equal to, less than or equal to situation, but we're just going to use equal to. So we're saying, okay, let's let you guys in management assume that you're correct, and the proportion that she makes is truly 0.427. So we want to see how this compares to that. That's what we're going to do through calculation. So that's the null hypothesis. Her true proportion is actually 42 points, or true percentage is actually 42.7%, or proportion equals 0.427. Now the alternate is the other claim. So the alternate is a statement about a change or about a difference. So when we're working these, you're still working off of population information. Okay, so we're going to use we're going to compare our sample or our study to what we expect to be going on in the population. But our statements need to be about the population. So it still always uses population information but some form of inequality. Some form of inequality, okay? So alternate's going to say that, yeah, we're different than what you've claimed originally. So what inequalities? Well, you have two different ways that a test can go. It can be one-sided alternate or a two-sided alternate. So one-sided alternate is pretty straightforward. You're either less than what they think or you're greater than what you think. Okay, so we would just be using one side of our sampling distribution. So that's just less than or greater than. Well, what do you guys think about a two-sided alternate? What form of inequality would show that you're a two-sided inequality? You're not just best, you're not just worse. Maybe we just don't know. We think there's some difference there, but we're not sure what that difference is. We don't know if it's higher or lower. Yeah, so a two-sided alternate would be a not equal situation. So just not equal to. So that's a case where literally we're just asking for, is there a difference between what we think is going on and what they claim? So if it's directional, it's one-sided, it's less than or greater than. If it just says that she's different, that's going to be two-sided. Well, in our study, we indicate that she's gotten worse, right? They're concerned that she's lower than what she used to be. So the alternate hypothesis is that her proportion is actually less than 0.427. Notice how I use the exact same parameter, population proportion, and calculation. Those don't change. The only things that change are going to be the inequality or equality statements. So that's how you write kind of just a really generic or really general hypothesis statement. They get a little more precise the more the complex a study gets, but this is kind of the general idea. No hypothesis says there's no difference, right? We're going to play devil's advocate. Alternate says, yeah, we think there's some kind of difference, maybe less, maybe greater, maybe just different, we don't know. All right, so let's jump in and see what the components of a statistics test or a significance test look like. Okay, so here's what we're going to work with when we do significance tests. We're not going to go through calculations today. I'm going to go ahead and tell you the values and we'll just kind of work with them. So in a significance test, we're going to have two values, a test statistic and a p-value. And again, we've actually worked with these, you kind of actually generated these before without realizing. So a test statistic, all it does is measures the difference between the observed data and the null hypothesis measured in standard deviation. Okay, the difference between observed data, so what we saw in our sample, versus the null hypothesis, what we're saying is happening in the population. So we really want to know how far these two measures are from each other, and we're just measuring that distance in standard deviations. Now, we can give it, we can have direction with it, and that kind of gets us towards our one-tailed test. So if it's negative, it'd be less than, greater, it'd be positive, that type of idea. But it's nothing more than distance between what we observed, what we expected, which was the null, all measured in standard deviation. In this one, because we're working with z. We can do the same thing with t-distributions or chi-square distributions when we get to those, things like that. So once we have a test statistic, so let's say that we have our test statistic. Sorry about that. Let's say that we have what we're observing. So our sample, null hypothesis said that she's a 42.7% free throw shooter. Our sample was somewhere down here at 0.303. Right? This said in the sample she was only 30%. We're just measuring this distance right here. So if we were to think of this in standard normal, the center will be at 0, so mu is 0. This would have a z-score of, that's what the negative 1.440 represents. So that's the z-score of this test, of our sample data, as it relates back to the standard error of our sampling distribution. So with that, just like we would any other normal stuff, there's a probability associated with it. So we have this area down here. So if this represents every possible group of 33 shots she could take. So we just we took every shot she's ever attempted or will ever attempt, and we put them into every random chunk of 33 shots. This tells us how many of those shots down there, or how many of those samples, chunks of 33, would have been less than 30% success rate. So that's what we're looking at right here, this area down here. Now this area is our p-value. Okay, that's, if you think back when we talked with sampling distributions, we call it sometimes the randomness probability or the random chance probability. That in this case works out to 0.0749. So if you were to do if you want to know the calculations, if I was to do a normal CDF on this problem right here using negative 1.440 and doing a left tail test or left tail calculation, it would give me that area of 0.749. So remember, this is all possible samples of 33 attempts, and then this down here represents, out of all those samples, the proportion of them where she made 30% or less, which is what she did and what we observed. So that's all p-value. It says assuming the null hypothesis is true. So assuming the null is true, that means we're using null to get our standard deviation of our statistic. That means we're using null as the center of our sampling distribution. So assuming the null is true, we'll let you guys be right, and we'll assume she's a 42% free throw shooter, or should be. Now let's figure out, does this sample back that up? So assuming the null hypothesis is true, the p-value indicates the probability of recreating results just like the observed data, or more extreme, through random chance. So if we randomly selected surveys or samples, what proportion of those would be 30% or less success rate for her? So that's what we're showing right here with our p-value. This is a number we're going to calculate through a little formula. It's really just your z-score formula in this case, or your standard, z-score formula. And then you're going to get a p-value. So then you're going to just do an area of a normal curve or a t-distribution or chi-square distribution. So those different distributions are the way these are calculated. So a manipulation of our z-score formula, and then some type of area calculation based off the distribution that we're looking at. So don't stress too much on the calculations right now as to what they mean. All right, so let's interpret what this means. So in this case, assuming the null hypothesis is true, well, what is the null hypothesis? Well, we said that the null hypothesis is she's a 42% free throw shooter. So assuming Carrie truly is a 42.7% three-point shooter, then the probability of her making 10 out of 33 attempts, right? That's what she shot. She came back from her injury. She had 33 attempts. She only made 10 of them. So the probability of her making 10 out of 33 attempts or fewer, right, or more extreme, that means from here to the left, by random chance, is the p-value. 0.0749. So there's a 7.5% chance that randomness can explain why she made 10 out of 33 and not there being some residual issues from her injury. Now we've got to decide, is that 7.5% chance that randomness is the explanation a large enough probability that we need to be concerned with it or not concerned with it? That's where significance level comes in. So significance level really is just the value that we compare our p-value to. So with significance level, I like to think like a significance threshold. Significance threshold. How much can randomness be the explanation? So how do you decide? Well, a lot of times you guys are going to be given this value in your AP stats and you're having to do these calculations on the AP exam. You're going to be given that, but kind of in real practice, this is a value you pick. You pick it at the beginning of the study before you do anything, and you're like, all right, I'm going to be okay if randomness were the explanation 10% of the time. I'm going to be okay if randomness is the explanation 1% of the time. You kind of look at the stakes of what it is you're trying to study and then decide how important that is. So in other words, how often am I comfortable with being wrong in favor of the alternate? So how often would I be okay getting it wrong by saying she actually is worse than 30 or 42%? That's what we're trying to decide. So there are a couple values you could use. First off, significance level, the variable we use for that is alpha, the little Greek lowercase alpha. And it's just a number you pick once you've answered that question. Typically, what we'll do is if it's stuff that's really not important, you'll see something like a 10% significance level. Things that have like maybe money related or economic issues, you might be looking for a 5% significance. I'm only being okay jumping to this or making these changes if I'm wrong 5% of the time. Things that are like life and death, maybe vaccine trials, or maybe who knows, big, huge government decisions. Maybe we need in those cases to be 1% significant or 0.1% significant, meaning that if we're going to make this change, we better be really, really sure that we're not going to be wrong by making the change. And that's what your alternate is. We're making the change. So if I'm wrong by making this change or assuming that I should have made the change, how often am I okay? So as the stakes increase, your significance level is going to get smaller and smaller and smaller. Or that's your comfort level with being wrong by assuming we need to go with this change, whatever the alternate represents. So how do we kind of work through that? So let's just pick a couple. So let's say that we picked a significance level of 0.10. Okay? 0.10 was our significance level. So if that was the case, if our p-value of 0.749, 0.0749, if it actually is less than our significance level, then what we would say in this case is we would reject, okay? So since P is less than alpha, we reject the null hypothesis. Which would tell us that we do have evidence for the alternate. So in this problem, I picked that 10% threshold, and I told myself before the study, if the randomness probability comes out less than 10%, we're going to say, no, she's no longer a 42% free throw shooter. She actually is much worse. And then we can go through our contract negotiations from there. So that's what that means. P-value is less than significance level, is less than my comfort level of being wrong, then I got to reject the null and I got to say, okay, this is actually going to happen. The alternate probably is more likely to be true in this case. Now, notice that we're not accepting the alternate. We're rejecting the null, the status quo, and we're coming to the conclusion that we do have evidence for the alternate. Well, let's say the reverse case is true. What do we do when the p-value is greater than or equal to significance level? So what if we picked a significance level of, say, 0.05? That's a pretty big economic impact. This is a really big deal. If we get this wrong by making some kind of change, then it could really set us back for a long time with these basketball contracts, or really hurt our business. So we really want to be sure that we get it right if we're going to get rid of somebody that's been so good for so long. So in this case, when P is greater than significance, well, that means that we're just leaning towards the argument that randomness is the explanation instead of there being something that needs to change or has changed. So in that case, if we think that it's a really high probability, that's what higher than significance. If it's a high probability of randomness being the explanation, then we're going to fail to reject the null hypothesis. That's the phrasing we use. Fail to reject the null, which means we do not have evidence for the alternate. Do not have evidence for the alternate, because the evidence isn't saying that she's actually worse than 42%. The evidence for us is that this is a high probability that randomness is the explanation. Maybe a little shooting slump, something like that. Maybe she's done these a few times throughout her career and it just happens, but she's still really who we think she is. So that's how you're going to pick it. You pick the threshold, or if you're taking an exam, you're going to be probably given the threshold. But these are usually the common ones that we do. So you would pick a threshold and then just see how your p-value compares to it. P is low, reject the null. The P is high, fail to reject the null. We don't accept alternates. We don't accept nulls. We just reject or fail to reject. All right, so let's jump in and talk about how we can kind of get this wrong. Obviously, you're talking about probabilities. There's error built in. There's the chance that you come to the wrong conclusion based on what's really going on. So let's talk about error in these significance tests. So there are two ways that we can kind of come to the wrong conclusion based on what's going on in reality. So in reality, the null is either going to be true or it's going to be false, right? It's got to be either correct or incorrect. And then the fact that we're either rejecting or failing to reject that means that we could get wrong. We could misread that probability. We could really just have found a sample that fell into that really extreme randomness area that shouldn't be explained by randomness, but we know anything's possible when we talk randomness. So the two errors I can have, it's a type 1 error or a type 2 error. So type 1 error means coming to the wrong conclusion in favor of the alternate. Coming to the wrong conclusion in favor of the alternate. Well, what's that mean? That means that we reject the null when the null is actually true. Or in other words, we get rid of a good null. We rejected by accident, and we misread things. So we rejected by accident. So our P was really, really low. We thought randomness could not explain what was going on. The null had to be wrong, so we rejected it. When it turns out randomness really was why we got the study and the results from our study that we did. So rejected the null. So reject the null hypothesis, but the null was true. That's going to be type 1 error. Well, the other type of error that you could have would be obviously type 2 error. Now, type 2 error means that we came to the wrong conclusion in favor of the null. Came to the wrong conclusion in favor of the null. So what would that look like? So if I favored the null, but I shouldn't have, that means the null got kept. So we failed to reject the null when the null was actually false. So in other words, we kept a bad null. We failed to reject, but the null was false. That would be an example of type 2 error. So our p-value was really, really high in this case. So we were high, so we failed to reject the null. And so we're saying, okay, well, there's a high probability that randomness explains this difference, and maybe randomness wasn't the explanation. Maybe there was something going on that we should have. Maybe we didn't do a really good study, and we kind of had an error in there in just the way we collected. Maybe our sample wasn't truly representative. You know, those types of things. Maybe we just, you know, something went wrong in the data collection process. So it caused us to get results that were too close to what the null hypothesis stated, so we just said, all right, we're going to keep the null hypothesis. That's an error that could happen. Now, there are probabilities of these. Well, the probability of a type 1 error or type 2 error, we denote with beta. Okay, so beta is the probability of a type 2 error. And it kind of comes off of an alternate reality, right? We kept a bad null. So this is our sampling distribution. This is the alternate reality sampling distribution. We'll talk more about that in our next lesson, about how to kind of see these two errors a lot more visually. But what we need to get right now is that type 1 error is citing with the alternate by incorrectly, and then type 2 is citing with the null incorrectly. Now, if we're going to use beta to represent the probability of type 2 error, type 1 error, we already actually know how to represent that, and that's nothing more than alpha. So remember, we said that my probability, how often am I comfortable with being wrong? How often am I comfortable with making an error in favor of the alternate? Well, I decided I'd be okay if I made that error 10% of the time, or if I made that error only 5% of the time. So your significance level is your type 1 error. So that's what you're picking when you do a significance level. You're picking your type 1 error. Type 2 error is going to not come off of that same sampling distribution. It kind of comes off of an alternate reality sampling distribution because it's not built off of the null hypothesis being true. It's built off of the null hypothesis being a false statement. So reject the null, but we shouldn't have. So we got rid of a good null. That's a type 1 error. Kept the null when we shouldn't have. So we kept a bad null. That's a type 2 error. Sometimes we do get it right. We keep the null and the null is true, or we reject the null when the null is false. This right here actually has a name also. This is known as the power of the test. And we're going to talk about that in our next lesson. But that's it for significance tests and error in general. So significance test is just getting it written up in a formal statement with hypothesis statements. And then getting a test statistic, finding the corresponding randomness probability or p-value, and then comparing it to a significance level or a significance threshold. So that's it, and I will see you guys in class tomorrow.